Hello everyone, this is Dhanlakshmi, Assistant Professor, Triple Department from R&D Engineering College. And I welcome you all to this video. In my previous session, that is in my previous video, I discussed about Thevenin's theorem. And in this video, I would like to discuss about Norton's theorem, which will be helpful. Thevenin's and Norton's are very similar to each other, and they are the most significant theorems in circuit analysis. So in this video, we will see the Norton. We will discuss the Norton's theorem. So Norton's theorem, as I told you earlier, that is in my earlier video, I discussed about Thevenin's theorem, and in this video we will discuss about Norton's theorem. So when we see Norton's theorem, again the statement, Norton's theorem states that any two-terminal linear network with current sources and voltage with n number of current sources, voltage sources and resistances can be replaced by an equivalent source or equivalent circuit consisting of a current source in parallel with the resistance. So here the idea is again as like of Thevenin's theorem, it is very similar. In case of Thevenin's theorem, we will be reducing any two-terminal linear network which is consisting of n number of voltage sources, current sources and resistance into a single voltage source in series with the resistance. The same way in Norton's theorem, any two-terminal linear network with n number of voltage sources, current sources and resistances can be replaced by an equivalent current source. So current source and along with that a parallel resistance in parallel with it. And we know already that so always the internal resistance of a voltage source should be in series and internal resistance of a current source is indicated as a parallel resistance. Right? So therefore here the idea of Norton's is to reduce any network given to us into a single current source into a along with the resistance in parallel. That is its internal resistance in parallel. So that is called Norton's resistance. And here that current source, that is we want to find out the current source value, that is Norton's current, that will be found by having the short circuit, that is found by the short circuit current across the terminal. So in case of Thevenin's, where we found the open circuit voltage and resistance, the equivalent resistance, where we connected the equivalent resistance in series. In case of Norton's theorem, we are going to find out the short circuit current, that is our Norton's current, and again the same way we are going to find out the equivalent resistance. That equivalent resistance will be connected in parallel here. So for current source, the internal resistance will come in parallel. For voltage source, the internal resistance will come in series. Again, to have a better understanding, we can take a small example and we can discuss that so that it might help us to understand better. So let me take a small circuit. Let me take a simple circuit here. Let me take a simple circuit here. Here we can see that two loops are available in this circuit. And here, let me assume that this 6 ohm is going to be my load resistance. That is where I want to find out the current. So the intention here is to find the current in the 6 ohm resistor using the Norton's theorem. With the help of Norton's theorem, we want to find out what is the current flowing in this 6 ohm branch. So therefore, when we take this, there is a branch or the element where we want to find out the current or voltage, that we will be considering as the load element or the load branch. So here I am taking the 6 ohm to be my load resistor. That is this is going to be the load branch. So and once I identify the load branch or element, then I have to mark the terminals there. So let me mark the terminal here as A, and here let me mark the terminal as B. So now the intention is we want to find out what is the Norton's equivalent circuit. As we know already that any circuit, right? So here the intention is this circuit or network has to be reduced into a single current source. Has to be reduced into a single current source. Along with that, I should have a resistance in parallel. So this is our Norton's equivalent circuit. So any circuit or any network, two terminal linear network can be reduced into a single current source with resistance in parallel. So that is the idea of Norton's. So therefore here you can see that this circuit can be reduced into a single current source along with that a resistance in parallel, and this is what we call it as the Norton's equivalent circuit. This is our Norton's equivalent circuit. Here we can see. So we want to find out how we want to we just want to know how to get this Norton's equivalent circuit. So when we say Norton's equivalent circuit, that is nothing but the Norton current. That is nothing but the Norton's current and Norton's resistance. So now we'll see how to find out this Norton's current and this Norton's resistance. So the first step is to identify the load resistance or the load branch. Here the 6 ohm is going to be the load resistance element. So the first step is to remove this load resistor. So in order to find the Norton's equivalent circuit, first step is we want to remove this load resistance. And after removing that load resistance, we have to short that terminal. Right? So here the terminals are A. After removing the 6 ohm, after removing the 6 ohm branch, we have to make a short circuit across the terminal AB. Right? And we have to make a short circuit across the terminal AB, and whatever current that flows in this short circuit is what called as the Norton's current IN. So the first step is to remove the load resistor, and after removing the load resistor, let me mark the terminal to be A and B, and we have to make a short circuit across the terminal AB, and the short circuit across the terminal AB, and whatever current that flows in this short circuit is what called as the Norton's current IN. So our intention is to find this Norton's current, and then later on in the second step we will be finding the Norton's resistance. So let me go to the next step where you can see the circuit, the same circuit. So here is the point where we had our 6 ohm branch, where the 6 ohm is our load resistor. So therefore what we did here is we removed that 6 ohm branch and we made a short circuit across the terminal AB. And now the current flowing in the short circuit path is what called as our Norton's current IN. So the first step is to find this Norton's current. So in order to find the Norton's current, now if we absorb this circuit, we have to see how to find this Norton's current. So here, one thing, a very simple thing, what we can conclude is here from this 20 volt source, we have a current. So this 20 volt source will be giving out the current, and let me take that current to be I. So let me take that current to be I, and now this current I flows in this path. So after this path, this current I has now two options. Either it can go in 10 ohm, or the other way, it can go in both the paths, that is in 10 ohm as well as in the short circuit. But we know that the current choose the least resistance path. So that what happens here is all that current I will be flowing only in the short circuit path. All that current will be flowing only in the short circuit path, where no current flows in the 10 ohm branch. Therefore, where no current flows in the 10 ohm branch, because we know that current always chooses the least resistance path. So out of this 10 ohm and short circuit, which are parallel to each other. So across this 10 ohm, we have a short circuit path which is parallel. So obviously what will happen is this current will choose only the least resistance path. So therefore, all that current will be flowing only in the short circuit path, and no current flows in this 10 ohm branch. No current flows in this 10 ohm branch. So there is no current flow in this 10 ohm. Once we don't have the current flow in this 10 ohm branch, this branch is meaningless. So therefore, what we can do is we can remove this 10 ohm, because there will not be any current flow in the 10 ohm branch. So this branch becomes a useless branch. That is, it's a meaningless here. So therefore, no current flows here. All that current will be flowing only in the short circuited part. So therefore, if we redraw the circuit, it will be a very simple circuit where it is consisting of only the 20 volt source, and we have a 5 ohm resistor. We have a 5 ohm resistor, and we have a short circuit. So what we did, we removed that the 10 ohm branch, because there is no current flow in that 10 ohm branch, because to that 10 ohm branch parallelly we have the short circuit path. So therefore, when we have a short circuit path parallel to any resistor branch, then obviously all that current will be flowing only in the short circuit. So therefore, here you can see that here is my 20 volt source. Here is my 20 volt source, and this is our 5 ohm branch. And we remove that 10 ohm because there is no current flow in the 10 ohm. And here we have the short circuit current. That is, short circuit current is our Norton's current. Now the intention is to find this Norton current IN, and we know that the formula for current I is nothing but V by R. So from Ohm's law we know that I is nothing but V by R. So here V is nothing but 20, and R value is going to be I. So therefore 20 by 5 will give you 4 ampere. So here you can see the Norton's current is nothing but 20 by 5, that is V by R. Here the value of V, the voltage value is 20 and the resistor value is 5. So therefore 20 by 5 will give you 4 ampere. So therefore 4 ampere of current is flowing in this short circuit path, which is our Norton's current. So thus we got the Norton's current. And the second step is where the same way, for this circuit, it seems to be very simple, but the same way we have to find out the current in the short circuit part. So that is the idea. So in order to get the Norton's current, we need to find out the current which is flowing in that short circuit path. That is the idea. It depends, it varies based on the circuit given. It depends upon the circuit or the network. It won't be very similar to all the circuit. Based on the circuits, it might differ. So our first step is over. That is where we found our Norton's current. The second step is we want to find out the Norton resistance. So it is very similar to our Thevenin resistance. Like Thevenin resistance, here we are going to find out the Norton resistance, and it is very similar. As that your Thevenin resistance, here also we are going to find out the Norton's resistance. For that, let me go back to the original circuit. So this is the circuit given to us. So again in the circuit, what we have to do is we have to remove the load resistor, and here for finding the Norton resistance, we have to make the terminal AB open. Only for finding the Norton's current, we will short circuit the terminal AB. But for finding the Norton resistance, don't short circuit. It should be kept open. For finding resistance, equivalent resistance, don't short circuit the terminal. Only for finding current, we have to short circuit the terminal. Now let you keep the terminal to be open. So just remove that 6 ohm resistor, that is the load resistor, then keep the terminal open. And after keeping the terminal to be open, now look back the circuit and see the remaining portion of the circuit. Wherever you have the voltage sources and current sources, and all those sources have to be removed. And we have to keep this in mind. That is, whenever we remove a voltage source, that should be made a short circuit, and whenever we remove a current source, that should be made a open circuit. So therefore, if you see this circuit, we are removing the 6 ohm and we are going to keep the terminal AB open. And apart from that, the remaining portion of the circuit consists of this 20 volt. So this is a voltage source. So once we remove this 20 volt source, we have to make a short circuit. So that is what we have done here. So here you can see that you can see the circuit comes like this. So here is the thing where we had our 6 ohm branch. So we removed that 6 ohm branch and we have to keep this terminal open. So don't short circuit. Short circuit have to be done only for finding the Norton's current. For finding Norton resistance, keep the terminal open. So this is the place where you want to find out your Norton resistance. So you're going to find out the Norton resistance here. And when we see the remaining portion of the circuit, here is where our 20 volt. 1 second. So here is where our 20 volt source. So that 20 volt source can be removed, and in the place of 20 volt source, that has to be replaced by a short circuit. So that has been done here. So here we had our 20 volt source, and that we removed the 20 volt source, and that has been replaced by a short circuit. And if you see the circuit here, you can see that it becomes a very simple circuit where you can see this 5 ohm and this 10 ohm. This 5 ohm and 10 ohm are in parallel now. So once they are connected in parallel, you can solve using the resistance is in parallel formula. That is R1 R2 by R1 plus R2. So here the resistance 5 ohm and 10 ohm. Here the resistance is 5 ohm and 10 ohm are exactly in parallel. Why? Because the starting node and the ending node of both the resistors are same. So therefore we can say that this 5 ohm and 10 ohm are exactly in parallel. So once they are in parallel, you can solve that by using parallel resistance formula. And we know that parallel resistance formula, the resistances are when they are in parallel, the equivalent resistance will be R1 R2 by R1 plus R2. So therefore 5 into 2. So here you can see that R1 R2 by R1 plus R2. So 5 into 10. Once again, let me finish off writing this. So R1 plus R2. R1 plus R2. So therefore 5 into 10 by 5 plus 10. So that gives you 50. So when we calculate this, we got the resistance value to be 3.33 ohms. So therefore we just now found the Norton's current as well as the Norton's resistance. Norton current we got it as 4 ampere and Norton's resistance we got it as 3.33 ohms. So after getting the Norton current and Norton resistance, we have to frame the Norton's equivalent circuit. So here you can see that Norton's equivalent circuit will be consisting of a current source which is 4 ampere here, we got the value now, and the Norton resistance which we got it as 3.33 ohm, and we have to keep it in mind that whenever we draw a current source, this internal resistance should be in parallel. That is our Norton resistance here. So Norton resistance and Norton current. So current source should have its internal resistance in parallel. So the idea here is we reduced this circuit or a network into a single current source. So single current source using Norton's theorem. So that is the idea here is we have reduced this network. So you just mark the terminal A and B here. So here we can see that we have reduced this network into a single current source along with that a resistance in parallel, and this is what we call it as Norton's equivalent circuit. So Norton's equivalent circuit will be consisting of a current source and resistance in parallel. So in like this, any network, any two-terminal linear network can be reduced. Any two-terminal linear network can be reduced into a single current source and be reduced into a single current source with along with that a resistance in parallel. So like this you can connect and you can have your Norton's equivalent circuit. Once we got the Norton's equivalent circuit, now you can connect back the load resistor. So here the load resistor what we had is 6 ohm. So you just connect that 6 ohm load resistor back, and after connecting that 6 ohm load resistor, if the intention is to find the current in the 6 ohm. So now we want to find out what is the current flowing in this 6 ohm. So in order to find the current flowing in 6 ohm, we know that here we can use the current division rule formula to find the current in 6 ohm. Because here if you see the current 4 ampere, the 4 ampere from the source will be coming out here. The 4 ampere current source will be coming out here. So at this point, the current what we have is 4 ampere. And this 4 ampere current is now having two parts. It is having either it can go, this partial amount of current will be going in this resistor 3.33 and the remaining current will go in 6 ohm. So now you can see that 3.33 ohm and 6 ohm are in parallel. So therefore you can use your current division rule. And for current division rule, we know the formula that total current, for finding current in 6 ohm. That is the idea here is to find the current in 6 ohm. The formula is total current. The total current here is 4 ampere. So the total current into opposite resistance. For 6 ohms, we can see that for 6 ohms, which is the opposite resistor, obviously the 3.33. So for 6 ohm, the opposite resistor is 3.33. So the formula for current division rule is total current, that is total current here is 4 ampere. So total current into opposite resistance, where the opposite resistance is 3.33 by the total resistance. So when you take the total resistance, here the total resistance will be 6 plus 3.32. I will repeat the formula once again. So the formula for finding the current division rule is, using current division rule is total current into opposite resistance by the total resistance. So therefore, once we use this formula, we are getting that current value to be 1.43 ampere. So using current division rule, the formula is total current into opposite resistance by the total resistance. So for 6 ohm, the total opposite resistance is 3.33. So once by using this formula, we got the current value to be 1.43 ampere. So this is the current which is flowing in 6 ohm resistor. And once you know the current in 6 ohm resistor, we can also find out what is the voltage across 6 ohm. So V6 is nothing but the voltage across 6 ohm, and we know that voltage formula V is nothing but I into R. So I is nothing but the current flowing in 6 ohm. So I6 into R6, that is 6 ohm. So I6 into R. That is I6 value just now we got it as 1.43. So 1.43 into 6 will give you 8.58 volts. So this is the voltage across 6 ohm resistor. So once you know the current value, we can find out the voltage. So voltage is nothing but V is nothing but I into R. So therefore current I is 1.43 and the resistor value here is 6 ohm. So 1.43 into 6 will give you 8.58 volts. So like this we can calculate the voltage and current in the load resistor. So using your Norton's theorem. So Norton's theorem is the thing where any circuit or any network any two-terminal linear network can be reduced into a Norton's equivalent circuit, where Norton's equivalent circuit is nothing but a circuit which is consisting of single current source with a resistance in parallel. And that single current source is what we call it as Norton's current, and that resistance is Norton's resistance. So by this way, we can reduce any network into a Norton's equivalent circuit. So thank you.